So thank you for the opportunity to speak with you today. I've enjoyed looking around the facility here. It's truly impressive. I've known about McMaster for a long time, all the way back to Dr. Mo Elbastawi. He was a student, I believe, of one of my professors when I was in graduate school, Dr. George Tlusty. And so we have a combined heritage, I guess you could say. So machining is a passion. I'm going to talk today about the fact that machining is more than geometry, as much as we would like it to just be geometry. And one of the application areas that has found its way into machining is machine learning. And so I've been thinking about machining learning over some time. In fact, I'm joining you from Columbus, Ohio, where I just attended the Ohio State University Materials and Manufacturing Conference. Very similar forum to what we have here today. And I talked about the application of machine learning to machining. And when I did that, it reminded me that just before we were all sequestered at home during COVID, I was thinking about this topic, and our digital friend Alexa had just moved into my house. Anyone else live with Alexa at some point? Yeah, so my wife was okay with that, but I think other than digital, not okay. So on April 7th, 2018, so almost exactly 5 years ago, I had posed this query. So I'm going to hold this up through this microphone. Oh.
Parts.
Sorry, I needed to turn it up.
I'm not sure.
We'll try again.
Alexa, am I making accurate parts?
Sorry, I'm not sure.
Okay, so we still have to think about this problem, right? We don't have the answer yet, so we're going to continue our studies of machining and training students like we're doing here today, and so that's why I'm here with you today. Okay, terrific. So machining is more than geometry. We'll see what I mean by that as we proceed. So some of you who look a bit like me in age might have started your career with mechanical drafting. I did. I liked it. I actually thought it was kind of an artwork. And so we had pencils and mechanical pencils once it got really fancy, and vellums and white prints and blueprints, but that's all gone. And today manufacturing is a digital enterprise where we use solid models and software applications. So if we're going to machine parts, there are fundamental steps in the digital world. We have to describe that part using a computer-aided design, and we've seen that here today. We need to select the cutting tools that I'm going to use to remove the material in order to convert that preform, which could be bar stock, it could be a forging, a casting, and more recently an additively manufactured near net shaped part, and remove material to get the geometry that we want. To do that, we need to generate the tool paths using computer-aided manufacturing or CAM software, and then we remove the material. Okay, so that would suggest that it's just geometry, but if you're in the room, you know that's not true. And so there's lots of things that can go wrong. There's many a slip twixt the cup and the lip, right? So the machine tool may not follow the commanded path. I'm sure that's not true for any machine tools in this lab, but from my own experience, sometimes they don't. They have air motions, which could be quasi-static, so they change slowly over time, like thermal air motions, for example, or they could be dynamic, where we have high-speed contouring and the controller affects that positioning performance in the corners. The tool can wear out. I saw lots of studies which are going on here just to my right about learning about tool wear to assess it and figure out when we ought to be changing that cutting tool. That remains largely an empirical effort. I'd say we probably haven't solved the physics around that yet, but I anticipate that we will one day have predictive models. Vibration can be an issue. So that's where I spend most of my time, is thinking about the implications of vibrations in machining applications, and there's some of that work that's going on here as well. I was thrilled to see that. And then the machine tool itself requires preventative and predictive maintenance, and that's going on here too. I had not seen the lab, nor did I know what projects were going to happen before I made this presentation. So it was very nice to see that we're so closely aligned in the things that we're working on. Okay, so let's think about vibration in particular. So of all those things I just mentioned, I want to focus on vibration today. And so the sequence of events that we have here are shown in the picture. So as I mentioned, we have a CAD representation of the part. We select our cutting tools, but let's pause there. Once I've selected a cutting tool, I've put it in a spindle, I've mounted that, or I've put it in a holder, I've mounted that holder in a spindle, I have now defined a dynamic system. And when I've done that, the best use of that dynamic system depends on its vibration response. And so we need to consider that when we're selecting our machining parameters. One of the tools we can use to select those machining parameters is something we call a stability map. So that lets us identify combinations of machining parameters that gives us good vibration, the green dot, over bad vibration, the red dot. So in machining, the good vibration, and there's always vibration, is what we call forced vibration, meaning it repeats from one tooth passage to the next in milling, or from one revolution to the next in turning. The bad vibration is what we call self-excited vibrations, and I'll talk more about that, but we use a word called chatter to describe those self-excited vibrations. There are analogies in other disciplines. I flew here on an airplane. When I looked out at the tip of the airplane wing, it was doing this, just a little bit, but it was vibrating up and down. That's also a self-excited vibration. So I have a steady flow of air over that airfoil defined by the cross-section of the wing. And that steady flow of air is modulated into vibration near a natural frequency. That essentially is self-excited vibration. So I'll tell you how we get that in machining as we proceed. But okay, so given that that's the case, I need to use that dynamic information to select my machining parameters in the CAM program. And then once I've done that, then I move on to obtain the geometry that I wish. If, however, I have not selected machining conditions that give me stable machining or forced vibration, then I can get chatter, and that can affect geometry and surface finish and tool life and the health of my machine. Okay, so one of the things that's important in this narrative is the dynamic response at the free end of the cutting tool, or the tool tip. That dynamic response we characterize using something we call a tap test. We have an instrumented hammer, we excite the tool, we have a vibration transducer where we measure that response, and then the ratio of those two is something we call the frequency response function. And that's shown here graphically, but essentially what it shows is natural frequencies, stiffness, and damping ratios for each mode of vibration, and then I can use that information to select cutting conditions. So at the end of the day, all structures vibrate. When I first started learning about machine tools, I was focused on machine tool metrology. I morphed into a vibrations person. But the way I had machine tool metrology described to me was, you can think of the world as being made of jello. It's always moving, it always deforms, and everything matters. And so in machining, the reality is it's a structure and all structures vibrate. And so we have to think about that vibration response as we're trying to do our best work at machining. So let's talk a bit about the implications of vibration. So if we think very simply, just a cantilever beam. Let's say I had a machinist scale and I clamped it at the end of the table and I pulled down on the end of it and let it go. We know that it's going to vibrate, and so if I have the blue ruler there clamped on the edge of the table and I pull down and let it go, then I'll have a response that might look something like this. And so if I looked at the up and down vibration as a function of time, I could get a curve that looks like what we see on the right. And the time it takes that vibration to repeat is something we call the period of vibration. And if I turn that upside down, I get the natural frequency. So structures have natural frequencies that we need to contend with when we're selecting machining conditions. Now, what if I change the length of that ruler? So I just shortened it. Same ruler, same table, I just made it shorter. Now what we'd anticipate is that the time it takes to go up and down in one of its vibration cycles is different. And not only that, but the size of the vibration is different. So I have a different time period, a different natural frequency, and a different stiffness. That's why the stick-out length of our tool from the holder matters, and it's why it's so difficult to select machining parameters without knowing the dynamic response of your cutting tool. I'm going to be controversial and say if you don't know this, you're guessing. Okay, but it's more complicated even than that. If I did have that ruler and I clamped it on the edge of the table and I pulled down and let it go, there is that response that we would see. That's what we call the first mode shape, which is oscillating at the first natural frequency. But simultaneously with that mode shape, it's also oscillating at its second natural frequency. Its mode shape looks like this. It happens at the second natural frequency, which is higher than the first natural frequency. Simultaneous to that, it's also doing this. This is the next natural frequency and mode shape. And it turns out for continuous systems like a cutting tool and a holder and a spindle, there's an infinite number of natural frequencies and mode shapes. So it's a very complicated dynamic system that we want to leverage in order to select machining parameters. So the way I think about this frequency response function, which is this graphical representation of these system dynamics, is like fingerprints. So each time I put a tool in a holder and place that tool and holder in a spindle, I get a frequency, I get a dynamic signature, I get a fingerprint. And when I change tools or I change holders, I have a different fingerprint. That fingerprint is the frequency response function, and so it's the blue curve shown here in the top and bottom panels. Essentially what those curves mean, taller is less stiff and less damping, and left and right is the natural frequency. So if I have that information, I'm able to make educated decisions about machining parameters that I want to select. So if I change the length of that ruler, I now have a new fingerprint, a different frequency response function, and my best use of that cutting tool would be different. My only math slide is here. For some, they'll be rejoicing that I have some math, and some will be running out the back door. That's okay. Hold your seats. This is the only one. So we can represent that frequency response function mathematically, and the only reason I include this is so you can see the terms that appear: stiffness, damping, natural frequency. We're all familiar with those concepts. They show up when we do this measurement. So if I can get at that measurement, then I suddenly have a way to avoid the guesswork in selecting machining parameters as I'm writing my CAM program. Okay, so the same information is captured mathematically now that we showed with the cartoon of that ruler going up and down, and then I can plot those equations to get the frequency response function we've seen on the right. Okay, so we get that information by something that we call a tap test. So I have a hammer where I tap the structure. That hammer is instrumented. It has a load cell inside, so I'm measuring the force that I'm applying. And then I have a transducer that measures the vibration. What you see here is just an aluminum bar, the hammer that's going to tap that bar, and then there's an accelerometer attached to that hammer. So that lets me measure that vibration signature that happens in response to the tap test. So the sound's going to come up here, and we're going to hear a tap test in real time. So what you heard was the natural frequencies all at once, just like ringing a bell, right? Those natural frequencies produce acoustic waves that I can hear. The same thing happens in machining. When I hear the sound of machining, I'm either hearing forced vibration, good, or chatter. And if we had chatter happening across the lab, not that that would ever happen here, but if it did happen across the lab, everybody seated here would know there was a problem. It doesn't sound right. Okay, and so same thing here. We can use sound in order to assess what happens in machining. Okay, so once we have that frequency response function, how do we use that information? That's the stability map that I showed you earlier. And so let's talk a bit about machining dynamics, and we'll end up with a description of that stability map. So as I mentioned, cutting tools are designed to be stiff. and stiffer is better. But there is no infinitely stiff material. They all deflect when a load is applied. So as a mental model, you can think of a cutting tool and a holder and a spindle as a stiff spring. That's a better representation than thinking of it as being a rigid body. The workpiece can also be flexible. So I wish it were the case that we only had to worry about the cutting tool, but sometimes the workpiece can be the most flexible element in the system, and so I have to consider it as well when I'm describing the system dynamics. Okay, the other thing we have to consider is that I have this system that deflects when I apply a force to it, and I have a force. If I'm machining, then I'm removing material in the form of chips, and that requires a cutting force. So there's been lots of work which has been done to make models of that cutting force. A mechanistic approach is that we say the force that's required to shear away the chip depends on the chip thickness and the chip width, and we can use those parameters with cutting force coefficients that represent the material and the tool geometry in order to predict cutting force. So in milling, we have this force that's required to remove material, but that force is not constant like it might be in turning. In milling, we have teeth which constantly enter and exit the cut, and so we have this train of impulses. Essentially, it's like that hammer ringing a bell over and over and over again. And so that is very effective at exciting the structural dynamics of our tool, holder, spindle, machine system. And so we get a vibration response out. So cutting force looks like this. Each one of these is a tooth entry and exit, tooth entry and exit, as we're showing here for a down or a climb milling operation. And then we get a vibration response of that cutting tool because it's not rigid and because I have this train of impulses which is exciting the system. There's nothing like machining, right? Seeing chips fly off, there's nothing better. So that showed this intermittent cutting operation where I have teeth engaging and disengaging and creating a chip with each tooth passage. Okay, so as I mentioned, there's two main types of vibration in milling. There's forced vibration, which happens at the rotating speed times the number of teeth. We call that the tooth passing frequency. So that tooth passing frequency excites the system dynamics, but it repeats with every tooth passing frequency. So even though we have vibration, that's repetitive vibration, and it's okay. We call that forced vibration. We describe that vibration also using the frequency response function, and we have some size of the response which depends on the relationship between that tooth passing frequency and the natural frequencies in our system. The other type of vibration that we're interested in machining is called self-excited vibration, or chatter, as I mentioned. And so chatter is a case where I have some mechanism that modulates a steady input force into vibration near a natural frequency. There's actually lots of examples in nature. Whistling is a self-excited vibration, so I have a steady flow of air across my lips, but it produces an acoustic response. I can hear the sound because of that. Playing a violin is another example. I have a steady bow of the steady pull of a bow across the string, but that produces sound. That's actually a stick-slip phenomenon due to friction between the bow and the string, and that's why we rosin the bow. The airplane wing flutter that I mentioned is a self-excited vibration, and then chatter in machining. In this case, the mechanism is I have this steady input excitation from the teeth entering and exiting, but then that is converted into vibration near a natural frequency, and I'll show you how that's done in just a moment. Okay, so I showed you the example of this cutting tool removing a chip, and that requires a force to do so. However, because the tool is not rigid, I can think about that tool being supported by a spring and a viscous damper, like a shock absorber. So when the force is applied to shear away the chip, the tool deflects, and that causes the tool to oscillate. Well, the outcome of that tool oscillation is that those oscillations are imprinted on the workpiece surface. Well, if we're in a turning operation, eventually that surface comes all the way around and the tool encounters it again. That means that milling and turning has a memory. There's a feedback mechanism, and we know that any feedback system, if I turn the gain high enough, I can make it go unstable. And so in this case, the gain is the chip width or the axial depth in milling. And so as I change the spindle speed and the axial depth, this feedback mechanism can cause the system to go unstable. We call that mechanism regeneration, or regeneration of waviness. Believe it or not, this is all the way back from the 1960s that this was understood. Not a new concept, but the force that I have depends on the chip thickness. The chip thickness depends on the current vibration of the tool and what happened either one tooth passage earlier or one revolution earlier. So that's the memory in my system. And then the current vibration depends on the force. But the force depends on the current vibration. And so now we have this feedback loop that can go unstable. And really what it comes down to is, as I'm removing material, the phase between the vibration right now and what happened in the previous tooth passage or rotation in turning. So if it happens that I can match the tool vibration right now to what it was doing one revolution or cycle earlier, even though I have vibration, my chip thickness, which is this left to right thickness here, doesn't change very much. And so my force doesn't change very much, and I get stable cutting conditions. If it happens, however, that those are not aligned, the vibration now and the vibration earlier, then I can get a chip thickness that varies, gets larger and smaller. Well, as the chip thickness gets larger and smaller, so does the force, which influences the vibration, and so I can get this self-excited vibration phenomenon that we call chatter. So something we want to avoid, but something we can avoid if we understand the system dynamics. Okay, so those are represented in this thing we call a stability map. So on the vertical axis is my axial depth of cut. In CAM software, that would be my step down. The horizontal axis is spindle speed, so how fast is my tool rotating. And you can see there's two regions. There's a gray region and a white region. The gray region is where the combinations of axial depth and spindle speed would give me chatter. And the white region is where combinations of axial depth and spindle speed would give me stable machining operations. So if I had this information available to me when I was writing my part program, now I can have a much better chance of having high metal removal rates without chatter, and avoiding some of the trial and error where we write the part program, it goes down to the machine, we run the part program, that wasn't right, send it back up, try it again. Avoid those loops, reduces cycle time and reduces cost. So that's what we're after here. Okay, so let's say you're interested. How would I get that map? Well, I need that frequency response function. And so as I mentioned, I showed you the video of the tap test. We can use that in order to collect the information that describes my dynamic system. And then I need these cutting force coefficients that relate the force necessary to shear away the chip to the chip area. And so, okay, so if I have those two pieces of information, I can generate that stability map. And now I can relate it to the performance of my milling operation. So if I selected a combination of axial depth and spindle speed in the gray zone, that's where we would come up with chatter and we'd have the vibration that grows over time, bad surface finish, large forces, not good. If I was to select a region in a combination in the white region, on the other hand, that's where I have the forced vibration, consistent surface finish, good milling result. Okay, so now that I have selected my machining parameters, I've programmed my geometry, I'm ready to machine away the stock, then I can have the outcome, which is stable or unstable machining. So I prepared an example here for you. One of the things that we often do in machining is pocketing operations. So what I'm showing here is a tool path that is enlarging an existing pocket. And one of the challenges that we often face, even though we select the radial depth of cut, in this case this is a 25% radial immersion cut, with a 4 millimeter axial depth, so that would be into the screen. The blue circle is my cutting tool. I'm just not showing the 4 cutting teeth. As I traverse around this square, sometimes that radial depth of cut is what I told it to be. This would be the 25% radial immersion. But when I get into that corner, instantaneously it's not. In fact, for an instant, it goes all the way up to slotting when I get into that corner. So what are those implications in terms of my machining performance? Okay, so the first thing that I need is that fingerprint that we mentioned, the frequency response function. So in this case, I have a simple example, just one mode of vibration at 500 hertz with some stiffness and damping. And so that describes that blue curve, which gives me my system dynamics. Okay, so given that and the fact that I'm machining 6061 T6 aluminum, I know my force model, I can generate my stability map. And so what I wanted to do here was to show some results at different spindle speeds and some different stability maps. So the map on the left is what I get for 25% radial immersion. Remember, the vertical axis is axial depth, but each diagram that I've shown here is for a fixed radial depth of cut. So this is for that 3 millimeter radial depth. And what I can see is if I selected those three spindle speeds of 5500, 6400, and 7400, two of those would be stable. They're under that blue curve. One of those would give me chatter at 5500 RPM. When I get into the corner, on the other hand, and I have my entry angle increases because of the geometry of that internal corner, I could be instantaneously here at a 75% radial immersion. Okay, so now my radial immersion has changed my stability map. So you can see the height of these peaks has moved down. So 25% radial immersion, I can get that tall. 75% radial immersion, I can only get that tall. Now, left and right, these best speeds remain the same because they depend on the vibration response, not the radial depth. But okay, so now what happens when I get into that corner, two of my spindle speeds are unstable. I would get chatter. Only one of them is stable. That's why a lot of times when we're doing pocketing operations, we hear that squeak in the corner. That's chatter in the corner because the radial depth of cut has changed instantaneously. Okay, so what would the results look like? So on the left is my 25% and 75% radial immersion stability maps. This is for 5500 RPM. On the right, the top plot's showing me the radial depth of cut. So it's 3 millimeters until I get into the corner, and then all of a sudden it gets much higher, up to 12 millimeters when I'm into that corner. The bottom plot shows me the cutting force that I'm going to see with that end mill when I'm completing that operation. And so after some initial transients when I enter the cut, then I can see the force becomes non-repeating and very large, and then gets really out of hand when I get in the corner. So both of these would be chatter conditions. This is where I get bad surface finish. This is where maybe I chip a tooth. Because I've selected a spindle speed that's not stable for either the 25 or the 75% radial immersion. Okay, what if I went to the 6400 RPM choice now? In this case, I'm having stable cutting conditions for the 25% radial immersion portion of my cut. So now we're looking at the blue curve. I superimposed it on the red curve, which was the all unstable. So now we can see for this portion of the cut, I have repeating forces. It's at a consistent force level, all good. I get the surface finish I want. But now when that radial immersion changes in the corner, when I get this condition, I still go unstable when I get in the corner. That's the squeak, that's the chatter in the corner, and the reason I might have to come in and fix that corner when I'm all done. Okay, so now if I go to 7400 RPM instead, same radial depth of cut profile, but now the green response for cutting force shows me it's repeating here as I'm moving across, and I get into the pocket. There is a change in the force, but that change doesn't cause me these dramatic force oscillations. It's just a change in the cutting force because my exit angle has changed. And because of the broader sweep of the periphery of the tool, now I do not have, for a 4-tooth cutter, my teeth, I never have no teeth engaged in the cut. And so that's why the force no longer goes to 0 there. Okay, so That's good, and those are things that we actually understand, and the barrier today is just moving that into production and finding ways to do that, but we do have to teach the next generation so we can carry that technology forward for those who will move machine tool technology and development in the next years. So let's look at some of those efforts here. So one of the programs that I developed is called America's Cutting Edge. Maybe I can call it North America's Cutting Edge. So it's a workforce development program for computer numerically controlled machining and metrology. I just learned about a program here at McMaster University. It's very impressive, and I'll look forward to talking with the folks from that program more. In the similar setup that you have here in your outreach program, we have an online and an in-person component. For the online component, that's about 6 hours to complete it. We introduce machining. We have the online participants generate their first tool path. Once they've done that, then we go back and say, you know what, let's take a look at those machining parameters. So we provide an introduction to machining dynamics. I wrote an app that's released with the training that simulates machining force and vibration. So it does a virtual tap test. It generates a stability map, and then it lets you run simulations to see the force and vibration. It even plays the sound of the cutting force. So students maybe who have never been in front of a machine tool can hear the difference between a stable and an unstable cut. And then finally, we wrap up with machining costs, because in the end, if you're not doing it to make money, then you're at a university. After the students have done that, we have an in-person training opportunity. It's a 5-day program. We have 10 participants per session. It's also offered at no cost, where we have the students machine the components for an oscillating piston air engine. That's shown here in the lower left. So there's the solid model. So there's a base and a wheel and a valve body and a piston block. And then at the end of the week, they assemble that and we run them. The second online training we have is for metrology, or the science and application of measurement. That takes about 2 hours to complete. We show the many possible manufacturing measurements that you might see in a production environment, and then talk about measurement uncertainty. How much can I trust those measurements? So this is a map of the folks who have participated in our online CNC machining training. We're now at over 4,000 online participants. From all 50 states, we do have participants from Canada and Mexico as well. Our student to industry ratio is 73% to 27%. And then for the students, we have high school 2-year and 4-year students engaged. It leans heavily toward 4-year students because that was my audience when I started this 2 years ago. But we hope to increase the diversity a bit in those online participants. The most important thing about this, when you complete it, you get a digital copy of my Machining Dynamics textbook. It's a real page turner. So I'm sure that's reason enough for you to do the training. Okay, so we do the in-person training. We have a national network that we're growing of in-person training locations. We started in Knoxville with a community college, the university, and Oak Ridge National Laboratory. And now we've expanded to other universities. We're using a hub and spoke model. So we identify a university that offers the training, and then they expand into their local network of community colleges and high schools. My goal for this program is 10,000 online participants and a training location in all 50 states. We're about 2 years in, we continue to grow. I want to erase the challenges that we have in workforce around CNC machining before I'm all done. It's a big goal, but what I'd like to do.
1, go!
So as I mentioned at the end of the
yes, there we go, Don, you got a chance.
Their components. We do an assembly competition. We do a bracket style competition that comes down to the winner. This was the championship round right here. You see how they have everything laid out? We didn't tell them anything about that. They practice the night before, they decide where they want their tools, and the gentleman on the right won this one. He assembled that air engine in 53 seconds. That's our all-time record. During the video, you can see there was a drone on the table. They compete for that drone, and they will kill each other for a $100 drone. So if you give a prize and let people compete, they will engage. At least Americans, that's for sure. Okay. Hey, don't laugh at that. Okay. So here is our oscillating piston air engine, the 4 components that they machine. We have an aluminum component. This is the part that they program online, so they've already seen it. Within an hour of arriving at the facility, they are machining that part. So we engage them right away and get them going. Then this is a piston block. We do the pistons in advance because we don't do turning during the training. We do have them use special fixturing to drill that cross hole, however. There's a steel wheel, so that's our second material. And then we have a 3D printed polymer block for our valve block. Because of the internal passages, this is a push-pull reciprocating engine run off 90 psi compressed air. It was easier to print it, and then they just machine the mating faces. There's no seals in this engine, so it's all fit in order to get the performance. So on Monday, as I mentioned, they machine the base component. We talk about machining, M&G codes, and get all the students on the machine. On Tuesday, we talk about machining dynamics, work holding, how do we identify and use datums, and then we machine the piston block. On Wednesday, we talk about machining cost and additive manufacturing. They machine the valve block. On Thursday, we do a metrology review. They machine the wheel, and this is the first time they assemble their air engine. So they begin practicing. On Friday, we review that CAM Plus app and the implications of machining vibrations. We do an on-machine tap test and chatter demonstration. We have them swap parts and put their air engines back together. We let them put a logo to personalize their piston block and then do a program evaluation. So it's about 40 hours altogether through the week, and we keep them running all day long. For the metrology program, this one's also a couple of years old. We're closing in on 1,000 participants. This is no accident. Where these dots show up is where manufacturing is done predominantly in the US. So Texas does a lot of manufacturing, California, the upper Midwest, and then the East Coast. Not a lot here in the central US, and so we don't have a lot of students there. This was completely self-organized. I didn't do any patterned outreach. This is just where people joined, which was quite an interesting outcome. So we're also interested in promoting machining at the university level. And so this last year, we had the first Southeastern Conference machining competition. So if any of you have been to the US to an SEC football game, we say it's just different and it matters more. I don't know if that's true or not. I played college football, it turns out, football, not football. And so I played at a university in Philadelphia called Temple University, but we did play at Tennessee. So I've played in the stadium at Tennessee many years ago, 1990. Yeah, I'm really that old. And so in any case, the SEC is near and dear to my heart. When I finished playing, I actually had a tryout with the Calgary Stampeders. I almost came to Canada, but then I wouldn't have done machining dynamics. So I think things were appropriate. Really what happened is they cut me and I went back to grad school. So anyway, for this first SEC machining competition, we had 4 schools: Auburn University, Mississippi State, Texas A&M, and University of Tennessee. We took the SEC logo, we made it large, about this large, and separated it into 4 quadrants. Each one of those quadrants was just undersized from a 12-inch by 12-inch by 2-inch aluminum plate. And so what each team got was the design that they had to machine. You can see we did some lightweighting on the back. So this was a multiple setup part. And then they got to select their cutting tools and practice at home. And then at the competition site, they were given 4 hours from walking up to the machine to finishing their part. We timed it. We calculated the cost from their tooling and their machining time. And then we measured the part. So we had some GD&T specifications that went with that part, some surface finish requirements. We measured it, all put it into a rubric, and then ended up with a winner. And so that was back in November. We anticipate growing that competition to about 12 of the SEC schools in 2023. Eventually, I want to go to other conferences and have a national championship for machining. I'll let Canada participate if you ask me really nicely. So I'll let McMaster in for sure. Okay, so we held that competition. I have a real quick video here to show that result. One of the 4 teams won. I'm not going to tell you which team won just yet. We know the SEC is big in athletics. We're going to make the SEC big in manufacturing. We anticipate that the students that compete today and the students that we'll touch through programs like this will be reinvigorating manufacturing in the U.S. as they become the thought leaders and the company owners and the engineers that press us forward.
This type of event means that we are actually in the communities and understanding what is important to them and how we can do a better job matching our needs and our requirements to the capabilities and interests of the students, because the next generation is important for our national security.
Some of the challenges in industry today include supply chain issues, labor shortages, where our customers are having to do more with less. So that requires thinking about a problem differently. So university graduates from a lot of these schools that you see here today, they're developing these next generation of critical thinkers that can take a look at a problem and say, you know what, this is one way that we've always done it, and now we want to try it a different way.
As an engineer, working on the machine hands-on is actually the best way to learn. You get to do the actual work, you get to actually make the parts, you get to touch it, you get to simulate, you get to try out different strategies. This way, when you go into the industry, you really have an idea of what the industry is all about.
The event today is representative of what we need across this country. We are better when we join forces. We are unified. We're a strong chain together. We need to be able to recruit the next generation in. We need to be able to train them to higher standards. We need industry to be involved in that, to send that demand signal and create that close relationship with these next generation students. And it takes a united front to do that of all interested stakeholders in the space of manufacturing.
The winner is Tennessee.
I'm in East Tennessee for a reason. I'm here because there's a national lab, a top university, community colleges, high schools, industry. We have all these things that come together in order to produce an environment that makes competitions like today possible. Yeah, so boy, did I get a lot of shade from the other universities because I hosted and won. They were all convinced that I cheated. I will never again host a competition. In any case, it was a lot of fun. So we're also interested in reaching out to the younger generation. So this was a collaboration with the Public Broadcasting System, or PBS in the US, that has children's programming. This was a series called Job Pop, where they did short videos in a TikTok style. That's an app that does things on... in any case, to encourage sort of children from 5 to 12 years old to consider machining as a career choice when they might not have heard about it otherwise. The best thing about machining is that I get to make stuff in metal and other materials. At the end of the day, when I've produced something using a machine tool, I know that I've added some value to the world.
Machinists are the people who manufacture and create many of the items you use every day. But how do they do it?
Machining is taking a sharp cutting edge, removing material, and creating a new surface. You become a machinist by understanding geometry and math and machines, and then taking all of that knowledge together to be able to remove material using a machine tool to produce the part that you want.
Machinists use super precise measurements to make sure their tools cut exactly what they want to make. You probably know how to measure in feet or inches, but machinists measure in thousandths of an inch. That's thinner than a piece of hair on your head. Most machinists make between $37,000 and $60,000 a year and work with a team of professionals.
So in machining, there's lots of different jobs. I could be the person who designs the machine tool, I could be the person who selects the cutting tools, or I could be the person that actually runs the machine to make the parts. Cars, airplanes, plastic drinking bottles, almost everything you touch during the day at some point was touched by a machine tool.
Learn more about this and other jobs at jobpop.org.
Yeah, you can clap. It's okay. So the outreach activities are clearly very important. We need to regrow the machine tool infrastructure, particularly in the U.S. And so one of the efforts that we've put together is the Southeastern Advanced Machine Tool effort. And so this has a mission of establishing the Greater Tennessee Valley, which is like from Huntsville, Alabama up to Northeast Tennessee, as a leader in the U.S. for machine tools research, development, education, and training. That was funded by a grant from the Department of Defense, $5 million over 3 years. So it was a federal investment because it's important to DoD's mission to be able to machine components. So the key participants in this effort, University of Tennessee, that leads. We have a Manufacturing USA Institute called America Makes, and then Oak Ridge National Laboratory. So in collaboration with those leaders and about 50 industry partners, we have 3 pillars that we focus on. We do Sea Mountain develops, incidentally Sea Mountain, because the mountains are right next to where I live. So that's you can see the mountains. You can see the mountains here too. I was just learning this morning that ridge is for Niagara Falls. I'm going to go see Niagara Falls for the first time while I'm here. So thanks for the trip, Stephen. So we Sea Mountain develops. We do R&D. We train. So part of that ACE training that I showed you, and is in addition to other opportunities, and then we connect. So we put leadership together with industry and have discussions to improve everyone. So this shows the map of where we're located in Tennessee. We do training, as I mentioned, including cybersecurity, which is more and more important in manufacturing environments. We offer apprenticeships, and then we have about 50 partners right now. A subset of those is shown on the right. So I really appreciate your time today. I've enjoyed being here. I look forward to talking to you throughout the day, and feel free to contact me with questions. Thank you.